Huawei says it can build a chip that matches the most advanced processors on Earth without buying a single machine that makes them. The machine it can't buy costs around $200 million. It weighs about as much as 2 full-size passenger jets. And the US government made sure Huawei would never get one. So Huawei went a different way. It claims it can reach performance equal to a 1.4 nanometer chip by around 2031, using older tools that everyone said could never get there. That's not a typo. Here's the part that makes this bigger than one company. The whole chip industry has been playing the same game for 60 years. Make the transistors smaller, pack more of them in, get faster and cheaper at the same time. That game is running out of road, and Huawei, cut off from the best equipment on the planet, may have found a way to keep winning without playing that game at all. If that sounds unbelievable, good. Because the trick isn't about making transistors smaller. It's about something the whole industry has quietly ignored for years. It's about how far data has to travel inside the chip. And once you understand that one idea, everything about the last decade of computing starts to make sense. Before we get into it, this one took a serious amount of research to put together because the science here gets buried under marketing on purpose. Stick with me, because by the end, you will understand exactly what Huawei built, what it did not build, and the one problem that could still sink the whole thing. Let's start with the game everyone was playing. For about 60 years, chips got better because of one idea. It's called Moore's Law. The rule was simple. Every couple of years, engineers learned to shrink the transistors, which are the tiny switches inside a chip. Smaller switches meant you could fit more of them in the same space. More switches meant more power, and because they were smaller, they were also cheaper to make per switch. Faster and cheaper at the same time. That's the magic that built the modern world. Look at the numbers. Chips in the 1970s held a few thousand transistors. By the 2000s, they held billions. Today's most advanced chips hold hundreds of billions. Hundreds of billions of switches on a piece of silicon smaller than your thumbnail. That is the most successful trend in the history of manufacturing. But here's the thing, it's ending. Shrinking transistors used to buy you huge jumps. 50% better, double the performance. Now the jumps are tiny. TSMC, the company that makes chips for Apple and Nvidia, and almost everyone that matters, is fighting for about a 6% improvement in its next generation. 6%, down from the double-digit and 50% gains of the past. And it costs more than ever to get even that little bit. Think about that for a second. Building a leading-edge chip factory today costs around $20 billion. Designing one new generation of transistor can cost about $1 billion before a single working chip rolls off the line. You are spending more money every year to get less improvement every year. The magic that gave you faster and cheaper is now giving you a little faster and a lot more expensive. So the whole industry is stuck at the same wall. And into that wall walks Huawei, with both hands tied behind its back. Here is where it gets uncomfortable for Huawei. Starting in 2019 and 2020, the US government began cutting Huawei off from advanced chip technology. By 2022, it was essentially locked out of the best equipment on the planet. The most important piece of gear on that banned list has a boring name: EUV lithography. It's made by one company, a Dutch firm called ASML. No one else on Earth makes it. An EUV machine is how you carve the smallest features into a chip. It uses a kind of light so precise that only ASML figured out how to make it work at scale. Each machine costs around $200 million. Each one weighs roughly as much as 2 commercial airplanes, and Huawei can't buy one. Not now, not soon, maybe not ever. So how do you make an advanced chip without the machine that makes advanced chips? China's answer at first was to push older equipment harder than anyone thought possible. The chip factory that builds Huawei's processors is called SMIC. SMIC can't buy EUV either, so it uses the older tool called DUV lithography and runs the silicon through it over and over with a trick called multi-patterning. Layer by layer, pass by pass, it forces older light to draw finer lines. And it worked, sort of. SMIC reached roughly a 7 nanometer equivalent process this way. That was already surprising, but it has a ceiling. Every extra pass costs more money and adds more chances for a mistake. You can push DUV multi-patterning only so far before the cost and the defects make it pointless. Huawei knew this. Running the old machine harder was never going to catch the leaders. So Huawei asked a different question. What if the problem was never the transistors at all? This is the turn that changes everything. For decades, everyone assumed the way to make a chip faster was to make the switches flip faster. And for a long time, that worked. But look at your clock speeds. The speed of the chips in your laptop and your phone has barely moved in about 15 years. 15 years of almost flat clock speeds, while transistor counts exploded. Why? Because the switches were never the slow part anymore. Here is the real bottleneck. Inside a modern chip, the transistors don't sit alone. They're connected by tiny wires, and those wires span more than 20 layers of material. Data has to travel through that maze, and the further it has to travel, the longer it takes and the more energy it burns. Engineers call this signal delay. In plain terms, it's traffic. Your transistors can compute the answer almost instantly. But getting the data from one side of the chip to the other is like driving across a city in rush hour. Huawei put a number on it that stops you cold. It says more than 80% of the energy in a modern computing system is spent just moving data around. Not computing, moving. Over 80 cents of every energy dollar is spent on the commute, not the work. Think about how strange that is. You built a city of hundreds of billions of workers, and most of the electricity goes to the roads between them, not to the workers themselves. If that's true, then shrinking the workers even more misses the point. The problem isn't the workers, it's the distance. So Huawei stopped trying to shrink the transistors. It went after the distance instead. The idea is called tau scaling, and once you hear it, it sounds almost obvious. If data takes too long crossing a flat chip, stop building the chip flat. Stack it, fold it upward, picture a page of text. If two words sit at opposite ends of the page, your eye has to travel the whole width to connect them. Now fold that page in half. Suddenly those two words are almost touching. You didn't shrink the words. You shortened the distance between them by changing the shape. That's tau scaling in one image. Take the parts of the chip that used to sit side by side, spread across millimeters of flat silicon, and stack them on top of each other so the signal travels straight up instead of across. A signal that used to travel millimeters now travels microns. A micron is 1,000 times smaller than a millimeter. Same logic, same transistors, but the data commute collapses. And when the commute collapses, three good things happen at once. The delay drops, so the chip feels faster. The energy drops, because you're not pushing signals across a whole city anymore. And the heat drops, because energy you don't burn is heat you don't make. The early results Huawei reported are the reason the industry sat up. Its folded approach hit a density of 238 million transistors per square millimeter. That works out to about 55% more logic packed into the same footprint compared to building it flat. 55% more without a smaller transistor, without an EUV machine, just by changing the shape from a spread-out map into a stacked tower. And the headline claim, the one that made everyone argue online, is this. Huawei says that by stacking mature processes this way, it can reach performance equal to a 1.4 nanometer chip by around 2031, without EUV ever. Now here's where I have to slow down and be honest with you, because this is exactly where the marketing wants to fool you. Huawei is not making a 1.4 nanometer transistor. It cannot. It doesn't have the machine for that. So what does 1.4 nanometer even mean? Here is the secret the whole industry keeps quiet. Those nanometer labels stopped describing the actual size of anything years ago. When a chip is called 3 nanometer or 5 nanometer, there is no part inside it that is literally 3 or 5 nanometers wide. The number is marketing shorthand. It's a rough grade for how dense and how fast a chip is, compared to the generation before it. That's all. It's like calling a car a sports car. It tells you the class, not the exact width of the tires. So when Huawei says 1.4 nanometer equivalent, it isn't claiming a new kind of transistor. It's claiming that by stacking older, proven transistors into a tower, the finished chip can match the density and performance of what a 1.4 nanometer chip would deliver. It's reaching the same destination by a completely different road. And that distinction matters, because a lot of the noise online treated this as Huawei magically leapfrogging ASML. It didn't. It found a detour around the roadblock. But here's the part that is a genuinely hard breakthrough. And it's not the number everyone was shouting about. To stack chip layers on top of each other, you have to connect them. You need thousands and thousands of tiny electrical bridges running between the stacked layers, carrying signals up and down through the tower. How close together you can pack those bridges is called the bonding pitch. The smaller the pitch, the more connections you fit, and the better the whole stack works. Right now, the best in the world is around 9 microns. AMD uses roughly that when it stacks extra memory on top of its processors, a feature it calls 3D V-cache. Intel and TSMC are in the same range. 9 microns is the current frontier, and getting there was hard. Huawei is targeting 1.5 microns. 1.5. That is 6 times finer than what the best companies on Earth can do today. 6 times more connections in the same space. If the 1.4 nanometer number is the flashy headline, this is the real story. This bonding pitch is the actual engineering wall Huawei is trying to break through, and no one has done it at scale yet. Now, before you get too excited, let me give you the reason this whole thing might still fail. Because there's one problem stacking creates that shrinking never had, and it's the oldest enemy in electronics: heat. Think about what you're doing when you stack logic chips. Each layer of active logic makes heat when it runs. On a flat chip, that heat has a big surface on top, and a fan or a heatsink can pull it away. But when you stack a hot layer on top of another hot layer on top of another, the heat in the middle has nowhere to go. It's trapped in a sandwich. The outer layers can breathe, the layers in the center are cooking. That is the make or break problem for tau scaling, and Huawei picked the hardest possible place to prove it first. Its first target for this technology is a Kirin chip. That's the processor that goes inside a Huawei smartphone. A phone has no fan, it has no liquid cooling, it has a thin metal frame and the palm of your hand. That's it. So Huawei is trying to run its heat sandwich in the one device with almost no way to get rid of heat. If they can make stacked logic behave inside a fanless phone, they can make it work almost anywhere. If they can't, the whole approach stays stuck in big machines that can afford giant cooling systems. Right now, that problem is not solved, not at scale. Huawei has shown the density numbers and the roadmap. It has not shown a shipping phone that runs cool with a fully stacked logic tower inside it. So keep that in mind whenever you see the 1.4 nanometer headline. The claim is real. The demonstration is not finished. There's one more honest catch, and it changes how you should think about this whole thing. Remember the old magic of Moore's law? Faster and cheaper at the same time. Tau scaling does not do that. Stacking layers, bonding them at 1.5 microns, managing the heat, all of it costs more money, not less. So this is a different kind of deal. You pay more to get more performance. You don't get the free lunch of cheaper and better that ran the industry for 60 years. That's a real trade-off. And it means this path only makes sense when performance matters more than cost. In a flagship phone or an AI chip, maybe it does. In a cheap gadget, maybe it doesn't. And here's something the online arguments keep missing. Huawei didn't invent stacking. It isn't alone out here. AMD already stacks memory on top of logic in real products you can buy today. Intel and TSMC both have their own 3D stacking and packaging roadmaps. The whole industry saw the same wall coming and started building upward. The difference is why Huawei is pushing so hard. The others have a choice. Huawei doesn't. Cut off from EUV, stacking isn't one option among many for Huawei. It's the only road left, and necessity is a strong engine. So let's step back and look at what actually happened here, because it's easy to lose the shape of it in the details. The US locked Huawei out of the single most important machine in advanced chip making. The plan clearly was to freeze Huawei at the back of the pack, and for a while it looked like it worked. SMIC was running old DUV machines in circles just to reach 7 nanometers. The gap to the leaders looked permanent. Then Huawei changed the question. Instead of asking how to make transistors smaller, the thing it couldn't do, it asked why chips had stopped getting faster in the first place. And the answer wasn't the transistors. It was the distance data had to travel. Over 80% of the energy in the whole system spent on the commute. So Huawei went after the distance, fold the flat chip into a tower, turn a millimeter journey into a micron, pack 55% more logic into the same footprint, reach for a bonding pitch 6 times finer than anything the West has shipped, and aimed to match a 1.4 nanometer class chip by 2031 without ever touching the machine it was banned from buying. That is the story. Not that Huawei has won, it hasn't yet. The heat problem is unsolved. The 1.5 micron bonding pitch has to be mass-produced with good enough yields to matter, and yield is where clever ideas go to die. The 2031 target is about 5 years out, and a lot can break in 5 years. But the direction is what should get your attention. For 60 years, progress meant going smaller. Huawei is betting the next 60 years of progress will mean going upward, and it made that bet not because it was smart enough to see the future first, but because it was cut off and had no other move. Take away someone's easy road, and sometimes they find a road nobody was looking at. So watch 3 things over the next few years. Watch the yields, because a genius design that only works one time in 100 is a lab trick, not a product. Watch the heat, especially in that first fanless Kirin phone, because that's where this idea either survives contact with the real world or falls apart. And watch what AMD, Intel, and TSMC do next. Because if Huawei's stacking works, the companies that saw the same wall will race up the same tower, and they have deeper pockets and more machines. The machine Huawei can't buy still costs $200 million and still weighs as much as 2 jets. Huawei still can't have one, and it just told the entire industry it might not need one. The next 5 years will decide whether that was the loudest bluff in tech or the moment the whole game changed shape. Not smaller, taller.